Okay, so we're interested in understanding how the couplings in this Lagrangian, there's an infinite number of them, flow as we go to low energy. And there are two things that contribute to how the couplings flow in the renormalization group framework. One of them is interactions, and we will discuss that soon. So we'll come to interactions soon. But the second thing is dimensional analysis. That's much easier to analyze. And in fact, at weak coupling, dimensional analysis gives you most of the story. So let's start off discussing dimensional analysis. Okay, so remember that we typically use units where we set h bar is equal to c is equal to 1. So you can think we're measuring uh, length and time in the same units, and we're measuring energy and length in inverse units. So we need to pick what unit we'll have. Let's use length. L uh, is our unit. Okay, so we're going to measure everything. So lengths and times are measured using L, and energies and momenta are measured using inverse L. Good. So let's imagine that we have an area, okay? So if we have an area, that means L has the dimension of L squared. The area A has the dimension of L squared. And I'm going to imagine that I've got an area which is 1 centimeter squared. So how can I rewrite this? Well, I want to flow to longer units. So maybe I start off in my microscopic theory, where a centimeter is a reasonable unit of length. But now I've flowed to my long distance theory, and maybe now a meter is a better length scale. So I'll take 1 centimeter squared, so 1 centimeter squared, and I'll multiply by 1 meter divided by 100 centimeters. And of course, that's just one because 1 meter is 100 centimeters, and I'll square this. So the advantage of doing that is that now the centimeter over here cancels with the centimeter over here, and I land up getting 10 to the minus 4. That's what 1 over 100 is, meters squared. So what you can see is this got smaller. And so I want you to check this. Let's say that we flow to even larger lengths. Let's say that we now flowed to kilometers as our unit. You can check, and please check this. Maybe I made a mistake here, but I get that this should be 10 to the minus 10 kilometers squared. So what you can see is this gets smaller as we flow to large distances. Okay, so this is the idea. Now I've illustrated it very concretely here with area, which is a length squared. Let's try to introduce a bit of generality. So let's say we've got some observable O that we're interested in. And let's imagine that O has dimensions of L to the P. And for now, we'll leave P completely unspecified. So we'll start off, we'll say O is equal to, let's say, 1 centimeter to the P. And now let's do exactly what we did above. So this is 1 centimeter to the P times by 1 meter over 100 centimeters, and we will raise this to the power of P. Okay, so let me maybe make this a little bit clearer. I don't know whether this will be clearer, but let's just try. Uh, so it's 1 centimeter to the P, and we've raised this to the power of P. Good. Okay, so what will happen here? Well, this quantity will get smaller if P is greater than naught, because then we're taking this fraction, which is 1 over 100, and we're raising it to a positive power. It'll, of course, get bigger if p is less than naught, because then we're dividing by this small fraction, we're dividing by a small number, so we're going to get something bigger than 1, so it gets bigger. And if p is 0, it stays the same size. So it stays the same size if p is equal to naught. So we've got a nice classification of the behavior depending on how p changes. So this is what you should think. We're starting off with some microscopic theory. Maybe it's an atomic theory. So the natural length scale for an atomic theory would be 10 to the minus 10 meters. If you want to tell me something in the atomic theory, I want it in units of 10 to the minus 10 meters. So if it's an area, I want to know it in 10 to the minus 10 meters squared, so angstrom squared, because then I know how big it is compared to an atom. But if I've flowed with this atomic theory and gotten to the scale of everyday life, so it's relevant for my life, well, then I want to know the quantities in terms of meters squared, because those are the units that I understand that affect me in my everyday life. So that's why we're changing the units. And what we can see is if we have gone with a p greater than naught quantity, so something like an area, we can see that these parameters go to 0, so these really are irrelevant. What does irrelevant mean? These parameters flow and they get so small, I'm just going to set them to 0 and I'm going to forget about them. They're just not important for the long distance theory. So any parameter of the microscopic theory that scales with a positive power of length just doesn't affect the long distance physics. When it's something that scales with an inverse of length, this parameter will grow. This is a relevant parameter. These are the parameters that we have to pay attention to. They're the major players. They're the things that are getting big. So these are the parameters that determine most of the physics of the low energy description. And if it's equal to 0, so things don't get bigger or smaller, then we say that these are marginal. And those are parameters which do not grow. At weak coupling, the simple argument based just on dimensional analysis gives you, pretty much the complete description. It's almost completely correct. So at weak coupling, this description using dimensional analysis is really telling you how the low energy theory looks. So let's imagine that we're somewhere close to weak coupling. Then we can take this analysis and we can actually investigate this Lagrangian and we can figure out how many relevant parameters does it have, how many irrelevant parameters does it have, how many marginal parameters does it have. And this is going to give us some good insights into what the long distance effective theory is. So that's what we're going to do next.